Hello community, so great that you are back. We talk about the next generation of AI, the latest research, Stanford, Princeton, Cambridge, Yale, Harvard, MIT, McGill and Nvidia, all in one video. And we have 3 beautiful new publications in UC 2025-07-18. So let's have a look what they are cooking. In my last video, we talked here a singularity that was discovered. And you remember, here Dongji University showed us here a bilevel reinforcement learning. And at first we had an OGF LLM and then we had a logic generation LLM, and they worked together here, language to logic over a GRPO optimization, a joint optimization of multiple RL. And we said this has the potential because we break away from language, we go to pure logic. Now, guess what? Now the publication of Nvidia 2025, here July 18, is doing more or less an optimization of the reinforcement learning methodology. So how can you train on, 100,000 GPUs? Can we optimize the reinforcement learning code? And when you have a look, they go here now with a DAPO, a decoupled clip and dynamic sampling policy optimization, which is based on the very 2017 PPO objective from OpenAI. And you remember this because we talked about DAPO already a month ago on a theoretical level. And now, today, we have the publication by Nvidia that it implemented this in their new model. Great. But we are interested in the real foresight. Now, Stanford, MIT, Cambridge, Harvard, McGill, Yale University. What do they think is the future of our AI model? What will come next? And we have another publication, and the first one was from July 16, and this is from July 17, so this is today for me recording this. And you see here we have now MIT as the lead contractor, then Harvard, University of Cambridge, Princeton, ARC, and University of British Columbia. And you say, hey, wait a minute, ARC Prize Foundation? Yeah, absolutely. And you know what? These models published within 2 days are strongly correlated. And I would like to show you this because maybe here the general YouTube audience has missed out on the elegancy. Let's start here before I talk to you here with Francois. Whenever you see Francois here, oh yeah, you know exactly what we are talking about. We are talking here about assessment. Now, you find here in the title world models. And if you are subscribed and you have seen here my video where I talked about the importance of world model with memory and agent-to-agent and MCP protocol tools, or you have seen here from Harvard, DeepMind, MIT, the world foundation model video. So you know world models are extremely important in the development. And this new paper here about assessing here adaptive world models in machines here with the idea not of a classical benchmark, but now the benchmark becomes here a game that the AI has to play. So you see here, this is here the first paper that is absolutely fascinating. And they start easy to say, hey, a hallmark of human intelligence now is the capacity to rapid adaptation, solving new problems in unfamiliar conditions. And we know AI fails catastrophically if we are out of domain or out of distribution or out of probability. So they say now, hey, this adaptability is linked to an efficient construction and refinement of an internal representation of the environment. And they refer to this as, in general, as the whole AI community, as a world model. So this is the internal representation that your LLM has, how the world functions, how everything is connected to each other. And the authors tell us here we refer to this adaptation mechanism as a world model induction. Beautiful. And then they call here for a new evaluation framework. At first, because the models, the LLMs get better and better, so we have to develop better testing routines. And we want to assess here not just a general reasoning capability, because the next generation of AI will be so special, we have to test their adaptive world models within the LLMs to understand their AI performance in general. And you notice, now we have today the ARC-AGI leaderboard here, and you have here AGI 1 and AGI 2 here. And now, if you want, this new publication goes and tells us, hey, we go now for the next generation of tests of evaluation of benchmarks, ARC-AGI 3. So absolutely fascinating where here all the highly intelligent, if you want, benchmark gurus of the world come together and tell us, hey, we have a feeling what the next models will be able to achieve, and we have to design a specific test to test for their, should I say it, intelligence of the AI models, and this is how we do it. Absolutely fascinating. So here you have everything: MIT, Harvard, Cambridge, Princeton, ARC Prize Foundation with Francois, and the University of British Columbia. And looking forward, they say, hey, for us the most important thing is we have to look at the internal world models of the next AI systems, because this will define how intelligent those models will be. And in particular, if we put an AI here in a new environment, if we have it access to new real-time data here from the environment, how adaptive are those world modeling internal representation in AI systems? So a beautiful paper if you want to read more about the upcoming evaluation routines here for the next generation of AI. Yeah, if you have some doubts that our test will not be good enough, here's also another paper published here on July 17, 2025, Formula 1. And here you have another new upcoming benchmark here for algorithmic reasoning. This is purely based here on graph and highly dimensional graph substructures on topology and geometric insight. So this will be a test suite that is absolutely fascinating. And if you think, oh, what is the current performance of our best model? Here, I've given you here for this brand new Formula 1 benchmark, Grok 4, the heavy one, has exact 0 performance, not even one right answer. And O3 High, and O3 Pro, and Gemini 2.5 Pro achieve below 1% success rate. So you see, we have the new benchmarks coming up. Don't you worry, we are prepared for everything. But now let's come to the main paper, and this is fascinating in so many aspects. Let's have a look. This is it. This is now led by Stanford here, MIT, Cambridge, Harvard, McGill, and Yale University. And they have a topic, I mean, in my simple words, I would say how to build the next generation of AI models. The next ideas, how we build the architecture of those models. Because I think with the classical models, yeah, you see Nvidia is really optimizing now the latest bits and pieces. We need new ideas for the next AI generation. And they talk about this, and they say, hey, modeling here the open world, the cognition as an on-demand synthesis of probabilistic models here for AI. And you might say, hey, this sounds interesting. No? Yes, absolutely. Yeah, everything is explained here. I love this here in this simple visualization. Yeah? Now, interestingly, they have here, of course, here the Bayesian reasoning and the model synthesis architecture and the implementation. Great. But they start with human. Yeah? And they say, hey, great. We have now in cognitive science, so with humans, we hold that people reason and plan using here mental models here in their mind. No? These are nothing else than structured internal representation that mirror here aspects of the world that we as humans we are familiar with. No? And they have a crazy idea. And I say, what you have in mind is to build the next generation of AI more and more like we humans do problem solving and reasoning. And maybe we can build the world models now real close to the human mental models, to the human structured internal representation. Absolutely fascinating to read this if you know about, let's say, medicine, or if you're a neuroscientist. Real interesting. I will stay here on general terms, and just to give you here one sentence, they say, we hypothesize that human minds implement a model synthesis architecture using a global relevance function to construct an ad hoc symbolic mental model which permits locally coherent reasoning over selected variables. And if you say, hey, that sounds simple, congratulations, to me, I had to have a little bit of a deep dive to really, try to understand each and every segment of this sentence. So just either you jump forward the next 2 minutes, or we have now a detailed look what this means together. So at first here, ideal is, of course, You have here all the background knowledge that is possible here, and you evaluate all possible answers here in a Bayesian reasoning task with all available background knowledge. So you have extreme knowledge, you have extreme calculation. Hardly anybody does this. And we know that the humans definitely is not going, oh yeah, I remember when I was 5 years old, this was my background knowledge that I had. No. What humans do is construct an ad hoc. You give them a task, an ad hoc. We built a mental model. Okay, great. So now we build an AI that does the same. Now the fun starts. And they say, okay, so we propose now a computational implementation of this idea, of this model synthesis architecture, MSA, using language model to implement global relevance-based retrieval. Do you remember RAG? And a model synthesis, and we will use some probabilistic programming code to implement coherent world models. There you have it. This is all there is. But of course, how you do it and the way you do it is here the beauty and the elegance here of this new idea. And as you can see, in the implementation here, we have here a particular LLM, a large language model, and then we will have here code. Simple, a probabilistic program that will encode here this new configuration that the problem condition LLM defined, and we will get an answer that is now coded and calculated. So not the LLM is reasoning about it, but we will use tools for this particular world model calculations. So you see this MSA approach is now like modeling the human open world reasoning. And they say we break it up in two subproblems. Now, construct or synthesizing here ad hoc models. The humans do it. So our idea is let the AI do it too. Must include here all the relevant variables of the system, all the conditions, all the boundary conditions, everything, every given occasion that is possible, and reasoning within a model which can be implemented via a general code algorithm for the decision making. And this has been studied in cognitive science. And you might say, hey, this sounds familiar. Yes, of course. We have, I don't know if you're familiar here, for years, and this is also done by Stanford University in cooperation with Uber AI Labs here in San Francisco in 2018, we developed already deep universal probabilistic programming. Now, either if you go with this version, or if you want to go here have something embedded in Julia, this is a general purpose probabilistic programming system with programmable inference. We have so many possibilities how to code this in our system. So whatever you choose for your particular liking, what is the main idea? You ought to say we implement here a concrete instance here of MSA using here a probabilistic programming language. Nice. We call them PPLs. And they have a simple task now to express individual models, maybe world models now with the boundary condition, with their start conditions, with all their constraint, now as probabilistic programs that we can code and run, and using here a neurally guided program synthesis procedure consisted here by structured calls to an LLM to construct relevant mental models, like the humans do. And they say MSA implemented in this way have desirable general probabilities. But what you should remember, we only have a simple configuration, just a two-step algorithm. No? We have an LLM front end, and then we have a general purpose PPL modeling language, where the coding is happening for the reasoning, for the argumentation to find an answer. So the LLM does not generate the answer anymore. We move to code, to general code, to probabilistic programming languages. And I think this is a nice way, it's simple, but I like it. I think it's a good one for two reasons. It can understand here any problem you give it in plain English because it uses here an LLM, if you want, as a translator, from the normal human language to code. Not to the code in Python or C++ or whatever you use. No. To a probabilistic programming language. And then, if we have this model and we have our PPLs, those PPLs are really now, after so many years, flexible enough to describe almost any probabilistic system. We have libraries that are just unbelievable. Are they perfect? Not yet, but you know what? There is now a new, if you want, vector accelerating their development. And you might say, hey, wait a minute, but this is real similar what you told us just about a week ago, no? Because when we looked at, and you'll remember this at DSPY with a TP optimizer, and then I told you, and you asked me, hey, what's the difference between a DSPY 3 and a Lean 4 methodology? I explained to you the difference, what is a language model program in Python, and what is a mathematical theorem prover with its own language. And you know what? This new publication by MIT, Stanford, and whatever fits now perfectly in the middle. Why? It is not like DSPY that we operate here only with a language model in Python. It is not an extreme logic mathematical theorem prover like Lean 4. It is something in the middle. It is beautifully positioned here with a PPL in the middle. So we have now probabilistic coding that is not as, if you want, hard as a pure mathematical proof solver as a tool, and it is not as weak as DSPY 3, that it stays here more or less with a language model program and it's just coding in Python. We go now with a new code environment. And the authors tell us, hey, these choices correspond to two cognitive hypotheses they have, I don't know about this, how to accomplish this reasoning in the human mind. No? At first, what they need is a mental model that draws on a large-scale statistical representation. Let's say as a human, I'm suddenly finding myself in the Sahara, in a desert, and I have to do something. I have no idea about a desert. I'm lacking in my knowledge, the large-scale statistical representation of any knowledge about what is growing in the desert, how should I behave in a desert, what is the temperature in a desert, how can I survive in a desert. You see, so you have to have all this background knowledge about the domain that we are talking to be able to draw a mental model. And remember, this is just a model. A model doesn't need to construct here the complete planetary dependence of all parameter. A model can be a real local, a very highly specialized local model that is maybe looking only at the next, 500 meters times 500 meters. No? And second, they say that coherent reasoning, and this is a decision making for novel problem is, because I'm now in the desert, so it's a real novel problem, is now realized by probabilistic algorithms that run over the mental models, but I have now code, I have no algorithm that give me hard-coded results that I can trust, and not a next token prediction of an LLM that I cannot trust. Interesting to see here the next generation of AI in this particular idea. So if you want, we just have here the LLM and the intelligence of the LLM of GPT-5 just as a translator with its beautiful, huge statistical background knowledge as a code or as a representation, and it just builds mental models that it knows that another system can code. So this is just a translator, and the real reasoning and decision making is happening in code, but not in the normal C++ or Python code, but in probabilistic code. And the authors tell us, hey, when we use this from the Bayesian modeling now, is to build a system that, like human cognition, can operate here in free, open world settings. Unpredicted things can happen. We are not in domain, while still delivering here the natively coherent reasoning of probabilistic models. How elegant is this? I've heard this and I have to tell you this. You can compare this now, because our classical golden Bayesian modeling, what we went with up until now, is like, they say they're old models, no? Like handcrafted ships in a bottle. These tiny, tiny ships that you have, they built in a bottle, and you see this and say, amazing, how does this ship was put into there? Eh? It's like this. This is how the old Bayesian modeling. It's stuck. There's no adaptability. The ship will never leave the bottle out in the open ocean for the real world contact. It is in its protected shell of a domain knowledge that it is only designed to live over there. It has no functionality for the real world. And now the next generation of AI models will change that. Yeah. If you are here younger for AI and say, hey, what are you talking about a Bayesian model easily? Just give you some idea. You start with initial beliefs. No? You have a few suspects, but you're not sure. Maybe you think suspect A is slightly more likely to be here somehow involved in this. So you have initial beliefs. This is your prior belief. And then if you are a detective, let's say you discover a new clue, no? A fingerprint that is found at the sea, but it doesn't match suspect A, but you suddenly see, this is the fingerprint of suspect B. So suddenly you have evidence. So you have your prior belief. Now with the evidence you see, maybe I was wrong. So you update your beliefs, no? So your suspicion that suspect A goes way down, and the suspicion that suspect B was one here of those people goes way up. So this is now your posterior belief. And the Bayesian model, guess what, just formalizes this process using the mathematical language of probability. I can give you an example if you're really new to this, to statistics here. Imagine here, and I like this example, you have a jar R of cookies. Here you have 10 chocolate chips and 30 plain cookies. Oh, only 10 chocolate chips. But the jar B has 20 chocolate chips and 20 plain cookies. So now, if I close my eye and I pick one jar at random and hand you a cookie from it, you get a chocolate chip cookie. The question is, which jar did I probably pick it from? And now your brain, without doing any operation at all, immediately knows it's more likely to be jar B. Because here we have 20 chocolate chip and 20 plain, and here we have only 10. So from the probability, you know that the Bayesian model now formalizes and explains why. If you're not familiar, now you have a hypothesis, you have your prior, you have your evidence, you have your likelihood, and then you have your posterior. And here you have all the details here, really for this example here with the numbers. So you immediately understand here our classical Bayesian model. And Bayes' theorem is here a mathematical engine now that combines here all this expression I've given you here. And you see it has a simple mathematical connector. Now, what your authors here, Stanford, MIT, Cambridge University of Harvard, McGill, and Yale do is they do the same now on probabilistic models that they develop here to run probabilistic code on them. So we do have now an example, and they give you here the example. Imagine you are somewhere in nature and you have some Olympics, or you have some competition, some sport, and they go here with kayaking. And they say the hypothesis is, a state of the world is unknown strength and effort of all the players. We just say, hey, our hypothesis is person 1, Sam, is strong, person 2, K, is weak. The prior is the belief that any given player has an average strength. And then we get some evidence, because we have then the results of the game, and the evidence is that the team of Sam and K beat the team of some others. So you see the likelihood, the probability of that win given the player's hypothetical strength, which is the likelihood of them winning can be calculated. And then after observing here the result, the win, you can now update here the belief, and now you have a new posterior probability. But you know, all of these models up until now more or less are static models. But we were talking about human, and the human capability. You put me in the desert and I immediately have to find a way to survive. I cannot say, hey, I have a static brain, no? So I have no information. No, I have to adapt to this new situation. And we do the same now in AI. This classical Bayesian model could not adapt to canoe races or rainy days where the conditions in the environment changed. We have new parameters, we have new dependencies, we have new whatever. No, this was done for one condition only. And this MSA now solves by teaching the LLM how to write these Bayesian models automatically. You know, the LLM write code. If you use Cursor or Windsurf or whatever you use, or Claude code or Gemini code, it writes code. We know this. But now this is a very specific application to write these Bayesian models automatically. So what we achieve now with this MSA is that the systems become now suddenly adaptive to the real world feedback. And you know what? What a coincidence. In my last video, I already showed you a new adaptive multi-agent AI system that is adaptive on a different level of configuration and is self-learning. And this was by ByteDance. So you see all around the globe, wherever you're looking, the top research, AI research groups are currently all working more or less on the same ideas. Okay, let's go a little bit deeper. The LLM, what exactly does it do? It's kind of the architect, no? When it's asked to write you the PPL program, it makes critical decisions based on its background knowledge. Background knowledge is, I'm now in the desert. So the first question the LLM might ask, if I'm now the LLM, is, hey, what are the relevant parameters? Where am I? And for the story about the race of the kayak or the canoeing or whatever, yeah, it knows, the LLM knows from its background knowledge, from its parametric knowledge it was pre-trained on, that speed and strength and endurance are important factors for a race. The name of the team captain's pet might be not relevant as a parameter it has to include. So it includes now and it defines what are variables for strength and effort and whatever, and speed and endurance. And he now combines these variables to form here a model, a representation that we then can encode in PPL. But you might also ask, hey, what are the relationship between those variables? So what is strength related to endurance? What is speed related to endurance? Is there a reciprocal factor or whatever? So you see, we then have, it translates this into a logic of the code. Speed is a function here of two parameters, strength and effort. Great, that's all we need. Plus, what are the reasoning starting beliefs? You know, the priors from the classical Bayesian. Its background knowledge knows that human traits like strength are often distributed in a bell curve. Most people are average, within a few being extremely weak and only very few are extremely strong. So we have statistical information on a general set of probability structure. So when it defines here the strength variable, it chooses, for example, in the simplest way, a Gaussian distribution as a sensible starting point. So you see, the LLM is essential in this process. It takes my human prompt, the task description that I give here to the AI system, and converts it with all of its background knowledge. And I don't specify if it's raining on this day, if there are 5 or 6 or 8 teams here doing here the competition, or if the water temperature has any effect here on the speed of the endurance or how the people feel or whatever. It has to have this background knowledge, this diffuse statistical knowledge on the domain-specific characteristics of our systems, and it just translates this into a structured, logical set of rules. So we have an extreme filtering taking place because the LLM knows or has a world model that it understands what parameters are essential. And then the second part is our PPL inference engine. This is easy. This is here the perfect mathematician that only understands here the formal language of probability. Nothing else. This engine executes the model, applies the evidence, and simply computes, given the mathematical formula and given the parameter and given the dependencies of the variables, the final coherent answer. Full stop. This is it. You get a probability answer because we're using here PPL. This is it. So what is the summary? The complete picture? Easy. 4 ideas. No? Input, a messy, my English, real world story, my problem that I wanted the LLM solves for me. The LLM is the brain here with its huge internal background knowledge. GPT-5, for example, says, hey, I've read millions of stories about sport, about kayaking, and I know everything what matters. I know all the models, I know all the materials, I know all the best players, I know everything about it. And now I'll use that knowledge to design a simplified model of the specific situation that I described here in real world stories. So what the LLM is now outputting after it inputted my human language, The output is now here a structured PPL program. And like it's coding Python for you. And then the solver's job is simply run this program, execute this. And it says, hey, I run this program and I find the most probable answer according to these exact rules. So we have here exact mathematical rules, but remember we are doing here probability distribution, so we have probable answers. So you see the whole system, if you want, hinges here on the LLM being clever enough, having enough domain knowledge, having been trained on all the reasoning of these domain interdependencies. The LLM has to be clever enough to act here as an automated Bayesian modeler, using its vast implicit knowledge to construct explicit, solvable models, PPL code, for any new situation that it encounters in its adaptive real-world context. You put the robot out in the field and the robot has to manage to survive. And now the beautiful part is the new models like GPT-5 or, I don't know, Gemini Pro 3, we only need them for the first part of the next generation AI systems. Because they will not have the precision to do everything by themselves internally. So this is the beauty. GPT-5 only for the first part, and the rest will be done here in a way of probability distribution, statistics, mechanics, theoretical physics, code implementation. But AI will change significantly, maybe already this year. So there you have it. Those are the ideas about the next generation AI that we can expect. And this is the research from all the beautiful researchers here, Stanford, Princeton, Cambridge, Yale, Harvard, MIT, McGill, and Nvidia, how they are currently preparing here the next generation of AI. If you want to see more, why not subscribe? And I see you in my next video.